In this video, we're going to learn how to write a polynomial function that contains given zeros. So essentially what's going to happen is we're going to be given specific zeros that a polynomial function needs to contain, and we're going to write an equation that contains those zeros. So before we jump in and talk about how to write these equations, we do need to talk about something called the irrational conjugates theorem. And what you see on the screen here is the formal definition of this theorem. But basically what this theorem states is that say you have, a polynomial function. So you have your a sub n times x to the power of n all the way down to your a sub 0, whatever those are. So you have your polynomial function and it has all rational coefficients, which means that the numbers in front of x and the constant do not contain a square root. They contain numbers that can be written as a fraction. And say that you solve this polynomial and you find that one of the zeros, so say you find that a 0 is something like 3 plus the square root of 7. Say that is one of your zeros. What the irrational conjugates theorem states, and this is because of the quadratic formula, is that if we get a 0 that looks like 3 plus the square root of 7, there is also a 0 at 3 minus the square root of 7. So it's going to contain both, because if we were to complete the quadratic formula, we would have that plus or minus in our quadratic formula in front of that square root, and so we would have both. So as we complete our examples today, we need to make sure we've accounted for all zeros using the irrational conjugates theorem. So if we see something that contains a square root, we need to note that anytime there's a 0 that contains a square root, there will be a positive and negative version of that particular root. So let's jump in and try an example. So here it says we need to write a polynomial function with rational coefficients and the zeros of 3 and 2 plus the square root of 5. Now, because of the irrational conjugates theorem, we actually know that there's going to be one more 0. So it's going to be 3, which we can see here, 2 plus the square root of 5, and because of the irrational conjugates theorem, we also have 2 minus the square root of 5 as one of our zeros. So everything that we write in this next chunk needs to account for the fact that we have 3 zeros, including this one that they didn't specifically tell us that we find using the irrational conjugates theorem. So I'm going to start by writing my function into its intercept form, or what looks like its most factored form. And so here I know that my zeros are the opposite inside of the function. So I know that this would become x minus 3 because it's going to be the opposite of 3. So accounting for that one is pretty simple, and we've put that in there. Now what's tricky here is that typically when we find these zeros, they come from, a part of the function that is like something x squared plus something times x plus a constant, and we use the quadratic formula to find those particular values. We obviously don't know what that particular part of the equation looks like right now. So we actually have to take the same approach we just took with the x minus 3. We have to take x and we have to take the opposite, or subtract 2 plus the square root of 5. And then we have to take x minus, so the opposite of, 2 minus the square root of 5. So you can see how I snuck those in there, saying it's x and then the opposite of our 3 zeros. Now, I don't know about you, but having parentheses inside parentheses is something that I don't particularly enjoy here. So what I'm going to do is I'm going to distribute out this negative. So this becomes x minus 2 minus the square root of 5. And this becomes x minus 2 plus the square root of 5. And then this one stays x minus 3. So what I'm going to do next is I'm going to use my big distribution strategy to actually multiply these second two first. So because of the way that multiplication works, the order in which we multiply doesn't matter, but I want to show you what looks like kind of a magic trick as we multiply these out because of that irrational conjugates theorem. So we're going to take everything in this first parenthesis and multiply it by everything in the second. So here we have x times x, which is x squared, x times negative 2, which is minus 2x, x times the square root of 5, which is plus x times the square root of 5. We can't really do much more with that. Then we take negative 2 times x, which is minus 2x. Negative 2 times negative 2, which is plus 4. And then we take negative 2 times the square root of 5, which is minus 2 times the square root of 5. Then we take square root of 5 times x, which is minus, I'm going to put the x in front, times the square root of 5. Then we take the square root of negative 5 times this negative 2, which becomes a positive 2 times the square root of 5. And then negative square root of 5 times a positive square root of 5. What's interesting here that you might not remember from algebra is that, so this is going to become a negative obviously, and you have square root of 5 times the square root of 5. Well, when you multiply two square roots, you can actually change this to be the square root of whatever 5 times 5 is, which is 25. So this becomes minus the square root of 25 is 5. So that actually changes into an integer, which is kind of convenient. Now if I look at this, what I notice is I have a lot of opposites in here that cancel out. I have a plus x squared of 5 and a minus x squared of 5, so those cancel out. I have a minus 2 square roots of 5 and a plus 2 square roots of 5, so those cancel out. So all I'm really left with here as I combine my like terms are I have x squared, and then I have minus 4x minus 1. So what's really kind of cool about those conjugate zeros is that they do eventually kind of cancel out those square roots as you work backwards and try to find the equation. So here if we just bring down the rest of the problem, we have the x minus 3 and the f of x. So if we want to keep going and get this into our original polynomial standard form, now all we have to do is take everything in that first parenthesis and multiply it by everything in the second. So we take x times x squared, which is x cubed. X times negative 4x is negative 4x squared. X times negative 1 is minus 1x. And then we take 3 times x squared, which is minus 3x squared. Negative 3 times negative 4x, which is a positive 12x. Negative 3 times negative 1, which is a positive 3. And then from here, we combined our like terms, so we end up with, I see an x cubed, so that's accounted for. Then I have minus 7x squared. Then I see plus 11x plus 3. So we've been able to take zeros of 3, 2 plus the square root of 5, and 2 minus the square root of 5, and work our way backwards to find the original standard form polynomial function that these stemmed from. So let's complete one more example together. So here it says write a polynomial function with rational coefficients and the zeros 4, 1, and 1 plus the square root of 3. Now remember, because of the irrational conjugates theorem, that this is telling us that we have one additional zero. So remember, we have an additional 0 here that is going to be 1 minus the square root of 3. So we need to make sure that our function has all 4 of those. So if we start off, so f of x is equal to, here we have x and minus 4, x minus 1 because of the opposites. I then take x minus 1 plus the square root of 3, and x minus 1 minus the square root of 3. Now remember, before we talked about, simplifying these parentheses within parentheses, so this part really becomes x minus 1 minus the square root of 3, and this becomes x minus 1 plus the square root of 3. And then the rest of this remains the same. So what I'm going to do here is I'm going to focus in on this part with the square roots first, just so that I can make that a little less messy. So I multiply everything in the first parenthesis by everything in the second. So x times x is x squared. X times negative 1, negative 1x. X times the square root of 3 is plus x square root of 3. Then negative 1 times x is minus 1x. Negative 1 times negative 1 is plus 1. negative 1 times the square root of 3 is minus 1 times the square root of 3. And then I have minus x squared of 3 plus 1 square root of 3 because of the negative times the negative. And then this becomes minus, and that becomes the square root of 3 times the square root of 3, which is the square root of 9, which if I evaluate that becomes just 3. So now if I go through and I combine anything together that I can, I notice that I have some items that cancel out. So the x square root of 3 and the minus x square root of 3 cancel out. I also notice that minus 1 square root of 3 and plus 1 square root of 3 cancel out. I then can see some like terms that can be combined. So I just see an x squared, then I see minus 2x, and then I see minus 2. So I now have made this a little bit easier, and those square roots are completely gone. Now from here, I just need to multiply these through one at a time. So I'm going to start with these two because they're a little bit smaller. So I have x times x, which is x squared, x times negative 1, so minus 1x. Then I go through the next chunk, I have minus 4x and plus 4. So if I combined my like terms there, I have x squared minus 5x plus 4. So it's getting closer and closer to a polynomial written into standard form. The last thing that I need to do here is I need to multiply out these two parenthesis pieces. So everything in the first parenthesis times everything in the second. So x squared times the x squared gives me x to the fourth. X squared times negative 2x gives me minus 2x cubed. And then x squared times minus 2 is negative 2x squared. I move on to the second term. Negative 5x times x squared is minus 5x cubed. Then negative 5x times negative 2x is plus 10x squared. Negative 5x times negative 2 is plus 10x. And then I move on to the next one. 4 times x squared is 4x squared. 4 times negative 2x is minus 8x. 4 times negative 2 is minus 8. So now the only thing left to do here is to combine together all of my like terms that I see. So I start off with the x to the fourth. I then move on. I see negative 7x cubed. I then see, I have negative 2x squared, 10x squared, and 4x squared. So that becomes 12x squared. I then see a positive 2x and then end with that negative 8 on the end. So here we can see our original function of what we started with. We have x to the fourth minus 7x cubed plus 12x squared plus 2x minus 8. And if we were to now take this and then work to find the zeros, these are the 4 zeros that we would end up finding.